Hello, everybody. So good to be with you again. It's Professor Steve Rehse from the University of Windsor coming to you one more time for one of our fantastic DoD Virtual Great Lakes Region and Tribal Nations Open STEM Topic Zoom learning session. This is going to be our April edition of this DoD STEM Open Learning session. Very pleased that you could be joining us again for this series. We've got about one more going for the academic year, and then we're going to take a little break for the summer. So really looking forward to talking about something with you today that's going to be really, really relevant to the weather that we're seeing outside. So you guys know that I love to talk about physics, and especially the physics that we see in the world around us, and particularly in the weather that we see, because most of what we perceive as weather in our world is actually driven by atmospheric physics and geophysics, and all of that is completely describable with the laws of physics that we know. And it's really, really cool to see physics being exhibited so clearly in the world around us. So because it's April and it's a very, very stormy season, this very stormy, rainy time of year, I've decided to give a talk on something that we're all really familiar with at this time of year. So let's just go ahead and see if we can actually learn something about that today. So I've got a little talk for you all. So I'm going to share this talk. Here we go. So lightning and thunder is what I wanted to talk about with you all today. So very, very appropriate topic for this April stormy season. And I'm hoping by the end of this lecture, we're going to learn some things about what we're seeing up in the clouds and the skies around us. So as always, we have to start off with our land acknowledgement statement. So the University of Windsor sits on the traditional territory of the Three Fires Confederacy of First Nations, which includes the Ojibwe, the Ottawa, and the Potawatomi. We respect the long-standing relationships with First Nations people in this place and the 100-mile Windsor-Essex Peninsula and the Straits of Le Detroit of Detroit. And we're pleased that you're able to share your time with us as well. So today, I want to talk about these two things. On the left here, you are seeing undoubtedly, what is that? Yep, lightning. And I also want to talk about the thunder that goes with it. So let's just dive into it. What I like to do oftentimes before we start is, again, since these are talks specifically geared towards incorporating as much traditional knowledge as we can, I love this website, the Ojibwe People's Dictionary. I've got the link right there on the screen for you. So we're going to be talking about thunder and lightning. So I thought we'd start off with talking about the Ojibwe words for thunder and lightning. So here's this first one, again, coming from the Ojibwe People's Dictionary. And I'm going to press play, and it's good if you turn up the volume a little bit just so you can hear, we'll hear the word, and then I'll try to repeat it afterwards. And we'll learn the first word for lightning or electricity. Let's go ahead and give a listen here.
Wasigan.
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 Wasigan. Okay, lightning, electricity. And then here's a word, thunder. The closest translation at the People's Dictionary I could find was there is thunder. So let's go ahead and take a listen to that.
Animikika.
Animakika.
Animikika.
Animakika. Okay, so there we go. So Ojibwe words for lightning and thunder. Certainly something that everyone who's existed on the surface of the earth forever has experienced lightning and thunder in their time. So very important to learn all the different ways that all of our different cultures have actually come to understand the lightning and thunder. That's a very, very present in your life. So before we get into the physics, this is actually a great quote from Mark Twain, the noted American author and humorist. Twain always has the best lines about everything. So what Twain said is, sure, thunder is good, thunder is impressive, but it's lightning that does the work. And that's exactly right. You're going to see that in today's talk. Thunder's good, thunder's very impressive, it's what you hear, but it's lightning doing the work. So a perfect quote from Twain to get us started on this lecture. So first off, who out there knows what lightning is? I've got a video kind of showing in the background here. So go, if you're watching this with some other people, watching this with your parents, watching this with a friend, put it on pause. Talk about, what do you think lightning is? What's the best description of what lightning is? And if you came up with something like electricity in the sky, electricity flowing through the air, something like that, that's pretty close. That's exactly right. Of course, one of our goals for today is going to be to understand that a little better, but you're right on. So now someone else, maybe if there were two of you and somebody was able to articulate or verbalize what you think lightning is, who can explain what thunder is? They usually come together. So what is thunder if you've explained lightning? And yeah, if you came up with an answer that says something like thunder is the sound that the lightning makes, it is the audio signature of the lightning, it's the audible pattern of the lightning, that would be right as well. Which comes first and why? Well, if you were really understanding what the lightning and thunder were, then you know that the lightning has to come first. Again, Twain said lightning does the work, and the thunder will come afterwards because the thunder is the sound that the lightning makes as it's propagating through the atmosphere. So the lightning causes the thunder, so the lightning has to come first. Now here is a first kind of learning objective for the day, something I really hope you can come out of this talk with. How long after you see the flash of the lightning, which I'm kind of showing here, do you hear that boom of the thunder? How long does that take, do you think, in your experience with thunder and lightning? And that's a bit of a trick question because it really actually depends on how far away the lightning is before you hear it. And that's going to be one of our first rules. So I'm going to teach you how to learn how far away, how to evaluate or estimate how far away a lightning flash is from you based on its sound. So first, a few simple numbers. Light travels about 186,282 miles per second. So according to our calculations, even if you were 100 miles away from a lightning flash, and you can't actually see that far, so this is not really a good example, but pretend there was a lightning flash and you were 100 miles away. If you were 100 miles away, the light from that lightning bolt would reach you in 0.0005 seconds. So you would never notice that lag. For you, that's essentially instantaneous. The lightning flashes and that light from the lightning strike hits your eyes almost immediately. There's a short lag, but almost nothing. You would never be able to tell that your perception of the lightning flash is different from when the actual lightning flash was. But thunder is a sound wave. Light travels on an electromagnetic wave. Thunder is a sound wave. It has to propagate through the molecules of air in our atmosphere. So it travels much, much slower. In fact, it travels only about 0.213 miles per second. You can take the inverse of that number to get how many seconds it takes to go 1 mile. So what that works out to be is it will travel about 1 mile in 4.7 seconds. So that's how fast the thunder is going, 1 mile every 4.7 seconds. So a very simple trick that you can exercise next time you happen to be in a lightning storm is if you count the number of seconds between the flash of lightning and then when you perceive the thunder and divide that by 5, you'll get the distance in miles to the lightning. So again, 5 seconds is 1 mile. 15 seconds would be 3 miles. 0 seconds, very, very, very close. So keep in mind, you really need to be in a safe place while counting. This good tip coming from www.weather.gov. So if you see the lightning, you see it and you start counting 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, boom, there's the thunder crash. You count it to 5, that means that lightning bolt is 1 mile away. That you don't need a watch, you don't need a stop watch or anything like that. You can completely just do it just by counting. That'll give you a very good estimate of how far away that lightning flash is and whether you need to really take cover, because as that lightning bolts get closer and closer, they can be extremely dangerous. So you don't want to be near it. So it's really helpful to actually know, was that close or far? Because they're so loud, you oftentimes can't tell. Okay, so now we've taught one thing, which is how can you tell how far away lightning is? So let's start to get into what is lightning. And I'm going to be showing lots of slow motion videos in today's talk because it's really the only way to actually tell what's going on. When you see a flash of lightning in the sky, it's so fast you can't observe any of the dynamics of it. But there's actually a lot going on in that bolt. So if we can slow it down, slow it way down, we're going to see lots of interesting phenomena happening that are going to tell us exactly what the lightning is. And of course, it's just such a beautiful phenomena in the sky, as I'm showing on this looped video on the screen in front of you. It's just a fascinating, amazing, beautiful thing to watch. So let's try to dive into what is that lightning in the sky. So to understand lightning, you do need to understand the physics of the situation, of course. And one of the physical principles we need to understand today is something called electric charge. Okay, so electric charge is a property of matter. What are the other properties of matter? Something could have mass, It could have some magnetization. You know, it might have something that you call color. These are just properties of materials, and electric charge is one of those properties. So there are two varieties of electric charge, and we have given them the names positive and negative. And of course, usually they're represented by a little plus positive sign or a little minus negative sign. That's the word that we've given to these two opposite types of charge. Everything has charge. Everything in our universe has charge in it. Usually a thing has equal amounts of positive and negative charge. Any object, including like a pen or something like that, will have a ton of charge in it, but however much positive charge is, there is just the same amount of negative charge, and so it all balances out, and that makes the thing what we call neutral. So something that is equal amounts of positive and negative charge is neutral, and then you don't really notice that the charge is actually there, although it can actually have charge. If a thing has too much of the negative charge in it, then we'll just say that thing is negatively charged. And if it's negatively charged, too much negative charge, that's something you'll be able to measure, you'll be able to feel it, and it's going to do something because of that negative charge. If something has too much positive charge, we'll call it positively charged in just the same way. Because nature always wants to be neutral. It doesn't really like the condition of positively charged or negative charge. It would much rather have everything kind of be neutral. And because it wants everything to be neutral, charge will flow from one place to another to achieve equal numbers. So if you have one area that's got a negative charge and one area that has a lot of positive charge, it would like that charge to flow together so it can all scramble together and then have a net amount of just overall neutrality as those charges mix together. And so as that charge flows from the one region to the other to combine and become neutral, that's a flow of electric charge. And it's going to move from one place to another. And that's what we mean by electricity. That's really what electricity is, the flow of charge from one region to another to kind of achieve overall charge neutrality. And that's really what we mean by electricity. So that's a rule of physics. If you understand what electric charge is, then the rule you need to apply to understand lightning is what I have at the bottom of the screen there. Charge will always try to flow to neutralize the overall charge. That's the rule. So here's kind of an example of what that might look like. So this is a common battery, right? You've all seen this type of battery before. You all know what batteries are. You put them in your electric devices, toys, rechargeable devices, whatever. If you look on that battery, it'll have a plus sign on one end. That's the positive end. It'll have a negative sign on the other end. That's the negative end. So positive charge, negative charge. Remember, electric charge wants to flow from the positive to the negative end to become neutral. Actually, in this case, we're showing it's flowing from the negative end to the positive charge. It's flowing in this direction. It wants to become neutral. And so we call that an electric current. So this battery has the two ends. If you connect them with a wire, current will flow, charge will flow from one end to the other. And that's what we mean by a current. And if we put that current through a light bulb, instead of just short circuiting it to the other end of the battery, that light bulb will light up. That is what we mean by electrical power. That's why you're putting these batteries in your devices. You're wanting it to do some work for you. You're trying to use the electrical power intrinsic to that battery to power a phone, to power a remote control, to power a handheld device, etc. So it's the flow of the current through an object that allows that object to use the electrical power. And the difference in the amount of charge between the two ends is called the voltage. That's the last thing you need to know. So again, you guys all know batteries. Batteries they always have a voltage on the outside. Usually a small battery is 1.5 volts. The square batteries are like a 9-volt battery, something like that. The higher the voltage, the more the charge wants to get from one end to the other. So the voltage is like how badly the charge wants to recombine. 1.5 volts is actually pretty low. 9 volts is much higher. On a 9-volt battery, the electricity really wants to get from one side to the other. It's like, you know, it wants to get there. It's about 6 times more than 1.5 volts. So roughly you could say like it's 6 times more effective at getting across from one to the other. And you can just do more work with that ability to push the electric current from one side to the other. So that's the idea that we call voltage. How badly does the charge want to go from one region to the other? High voltage, it really wants to move from one side to the other. Low voltage, not so much. So now we're talking about the flow of charge from one region of one charge to a region of another, and the voltage tells you how strongly does it want to go. Well, the ability of charge to flow from one region to another depends on what the charge has to flow through. It does have to flow through something. So does anyone out there know what type of material electric charge flows very well through? What classes of materials are very good materials for letting the charge flow through easily? Do you know? Well, one example of this type of material would be metals. Metals are very, very good at letting electric charge through them. For example, your house is full of copper wires. So these are copper wires, like that would be the wires inside your house. Electricity flows really, really well through copper, and copper is a type of metal. So electricity flows great through any type of material, and we call that material a conductor. So the answer to the question is conductors. Anything that electricity can flow easily through is a conductor, and metals are one great example of a type of really, really good conductor. It just means that if the electricity, the positive charge is here, and say it wants to get over to the negative charge here, it can do that easily through a conductor. The conductor says, yep, you're free to move through, no problem. It moves with very little resistance. Now, does anyone know what type of materials electric charge flows badly through? What do you know about that? I can give you one example of something that electricity flows pretty badly through. Wood is a good one. Dirt, clay, these are all good examples of things that electricity really does not like to go through. This is lumber. This is a 2x4. And if you put a bunch of positive charge, tried to put positive charge on one end and negative charge on the other, they would not be able to flow through the wood to get to each other. Remember what electricity wants to do. That's the rule. You have to learn the rules of physics. If they have a positive and negative charge, they want to come together to be electrically neutral. But if the thing that they have to move through to come together doesn't want the electricity flow, it's going to be a problem. This thing resists their flow. We call materials through which electricity flows poorly an insulator, and wood is an insulator, and dirt is an insulator, something like that, as opposed to the metals, which were conductors and allow electrical charge to flow really well. Okay, now we're getting to the lightning, I promise. So what about air? Lightning usually occurs in air. You've all seen the lightning, you know that. What about air? Is air a conductor or an insulator, as I've just defined those two words? What do you think? Well, turns out air is an insulator. It's actually a really good insulator. Electricity really does not like to flow through the air. In fact, most of the time it can. If I have a high amount of charge, say in this hand, and a high amount of the opposite charge in this hand, the electrical charge just cannot flow through the air between these two hands. It just can't. And that's good for batteries, because if you were just holding a battery and electricity flowed through air, the electricity would just flow from one end of your battery to the other, right through the air. And then the battery would never hold any charge. So they don't do that. Most of the time, electricity cannot flow through air at all. At low voltages, like the voltage in a battery, 1.5 volts, 9-volt battery, there's no way electricity can flow through air. It just doesn't. That's not to say that electricity can't ever flow through air. So air does not let electricity flow in general, but if the voltage is high enough, there's that word voltage again. So remember what I told you about voltage. Voltage is this idea of how badly does the charge want to go from one region to another. So something that's high voltage, you've really built up a lot of charge and it's really keen to get from one point to another, and that's a high voltage. So if the voltage is high enough, in any material, electricity can actually jump from a region of positive charge to a region of negative charge, or vice versa, right through the air. So if the voltage is high enough, electricity will kind of burst through the air, and it'll just actually blow the air apart and make a small ion channel through which electricity can flow. And anytime you've gone for a car ride, you're actually using this phenomena. This is something in your car called a spark plug. All right, if you could zoom in on the spark plug, you're going to see there's a copper core center electrode, this little copper thing here, and then it's this bent piece of metal, this platinum or iridium tip. And the idea is we're going to put a high voltage between the copper core center and the platinum or iridium tip. And you can see the air gap. This air gap is a very, very special distance between the copper and the platinum in this case. And electricity would normally not be able to flow through the air. But if you put enough voltage between the center electrode and that platinum tip. You can see what's happening on the screen. The electricity so badly wants to get from that center electrode out to the platinum tip, it jumps through the air. It literally jumps across that gap. And in that jumping, there's so much energy in it, it's actually tearing apart the air molecules. And you can see that on the screen. Can you see all that little, what looks like flame in the middle there? That's not flame, that's called a plasma. All right, the electricity is ripping through the air and it's ripping atoms and electrons off of all the atoms and molecules that are there to make an ion channel through which the electricity can flow. And it's kind of jumping around because this ripping, tearing process is pretty violent and it's not smooth or slow. It kind of occurs in a big burst and it rips everything apart and it kind of moves all over the place randomly. And you can see that in a spark plug. And the spark plugs in your car are firing many, many times a second, creating that little gap. And it's that little spark that actually ignites the gasoline in an internal combustion engine. The combustion of the gasoline is what powers the pistons. And for a gasoline powered car, that's actually what makes the car go. So this idea of the plasma is really, really important. And the fact that voltage can jump across the gap is really important. All right, here's another way you can get sparks to jump through air. Now, this is an experiment you can do at home. Many of you have probably already done this before. You can get sparks to jump from your finger to a doorknob. If you don't want to do it on your doorknob, when I was a younger child, I would do this on my brother, go around and try to shock my brother. So you can make static shocks with socks and carpet. So if you just put on a pair of clean, dry socks, that's the first part of this experiment. I was getting this all from www.wikihow.com, make static electricity. But when I was a kid, I didn't need a website to tell me how to do this. We just figured it out ourselves. So if you have a clean pair of socks, wool socks generally work the best. And then you scuff your socks across the carpet. So they're saying shuffle lightly across the carpet. It's just kind of scuffing your feet as much as you can. Walk quickly while lightly scuffing your feet across the carpet. This is going to pick up charge from the carpet and store it in your body. And you are now achieving an overall inequality of charge in your body, inequality of negative charge. So then you have an excess of negative charge in your body, then you have to just move a finger somewhere near a metal object. So the charge is uniformly distributed through your body, but when you put out a finger, I'm going to show you a diagram in the next slide. The charge in your finger, the charge in your body is going to rush to your finger because it wants to jump to a region of positive charge to overall neutralize itself. It's going to look like this. So you've got a bunch of negative charge all over your body that you've picked up by shuffling your feet. But as your finger gets close to the doorknob, the charges start to feel, oh man, there's positive charge in that doorknob. In fact, it repels the negative charges in the doorknob and draws the positive charges to it. And they really want to recombine. They really want to recombine. So all that excess charge from all over your body, you won't feel any of this. You don't feel any of it. It rushes all over your body and collects in your fingertip. And then when that gap between the fingertip and the metal doorknob gets small enough, you can get a little spark of electricity to jump from your finger to the doorknob. Or if you're mean, you can do it to your brother and kind of come up behind him and zap him. And that was always kind of fun. But make sure you get there, as they say, get the other person's permission for a touch them, because not everyone likes those static shocks. But that's exactly what we're talking about. If you guys have ever shuffled your feet across the floor and made a little spark come out of your fingertip, that's really all lightning's going to be, but on a much bigger scale. So how cool is that? You actually already understand the physics of lightning because you've been doing it a long, long time. So that's really what lightning is. It's electrical charge that's jumping through the air. That's really all it is. You add a little burst of electrical charge, a little plasma from your finger to the doorknob. Lightning is just that on a much bigger scale. So the only question then is, where did all that charge come from? Because when you were shuffling your feet across the carpet, we know where the charge came from. You're actually, by shuffling your feet, you're actually pulling free charge up from the carpet and pulling it onto yourself. But there's no carpet up in the sky. So where did that charge come from? And the answer is clouds. Always the clouds. If you ever see lightning, there's going to be clouds involved. You cannot go outside on a clear day and see lightning bursting from one place to another. It just doesn't happen. You might think it does. It doesn't. The lightning is related to clouds, even heat lightning. It's going to be high level clouds, always going to be some form of clouds. And here's why, because the clouds are the carrier of that charge. Here's a great example that's going to show you what you're seeing. So these are usually giant clouds, and the clouds that produce the greatest lightning bolts are going to be these big, big thunderstorms. So if you've ever seen a big thunderstorm moving in on the horizon, it's really, really tall clouds, 10,000 meters tall, something like that. And they have all kinds of charge distributed within them. And there'll be a center of positive charge and a center of negative charge, but it's going to be an interaction most of the time between this positive charge at the bottom of the cloud and say a negative charge on the ground. And so as the charges in the cloud feel the charges in the ground, they're going to pull themselves towards each other. And this can form what's called a cloud to ground lightning bolt. On the other hand, you've got regions of positive charge and negative charge within the cloud itself. So there's plenty of lightning. If you've ever been out in the evening and seen a storm cloud come in, you'll see lightning flashing within the cloud. That happens too. So within cloud lightning bolts, trying to equalize regions of positive and negative charge. You can have lightning bolt jumping from one cloud to another. So there's cloud to cloud lightning, again, from positive to negative. You can even have cloud to air lightning. There's so much, in this case, there's so much positive charge up here. The positive charge is just trying to get out. There's so much voltage, it just wants to blow its way out of the cloud. And so it's just kind of like shooting itself out into the air, looking for any charge that it can neutralize on. So within cloud charges or cloud to ground is mostly what you're going to be used to be seeing. And that lightning bolt, it can go from positive charge in the cloud to negative charge on the ground, or vice versa. It can go from negative charge in the cloud to positive charge on the ground. When you see a lightning bolt, ordinarily you're not really able to tell which one of those conditions it's doing. But remember, it's charges within the cloud that are trying to neutralize. They don't like having so much excess positive and so much excess negative in one spot. It would rather be neutral. So it wants the positive and negative to get together to form neutrality. But they want to get together so badly that they tear the air apart in the process of doing it. And that's really what lightning is. Now, I'm going to show us a few videos for you here. If you are interested in this topic like I was, this is an excellent 10-minute video from a YouTube provider called Pecos Hank, How Lightning Works, Weird World of Lightning. I really recommend this video to you all. If anything I'm talking about here is interesting, Pecos Hank goes into way more great details, just details that we don't have time about, but he's got some fantastic videos, great explanations, really in-depth stuff on the lightning. I really give him a high recommendation if you want to dive deeper into the world of the fantastic weird world of lightning, which is what he calls itself. So give his website a look if you want to learn more. So let's just take a look at a kind of a real-time lightning event here and just see what happens. Okay, so you're seeing all these flashes, right? See this? So within cloud lightning, see all that? Not much is even hitting the ground there. So all of these flashes in cloud, within cloud. So remember, there's regions at the top of the cloud and regions at the bottom of the cloud that all have different charge. They're trying to neutralize themselves. So he's calling this a cloud flash, intracloud lightning. So regions of one part to another. And it kind of looks like this. So you can see here's a region of negative charge. Here's a region of positive charge. The lightning bolt is the flow of electricity from one part of the cloud to the other to overcome that neutrality. So that's that within cloud lightning. Now, let's take a look at what happens for the lightning that's going to form, on the ground. Let's go ahead and just take a look at that. And I'll just pause that here. Let's go ahead and take a look. Okay, so what's going to happen is the positive charge, this is going to want to recombine with some form of charge on the ground, and he calls that a ground flash or cloud to ground lightning. So let's take a look at that in slow motion and see how that works. So he calls it CG on his website. So, all right, now look, it doesn't all happen at once. So as in this case, you've got a bunch of negative charge in the cloud and a bunch of positive charge down on the ground, and they can feel each other. They want to combine the negative charge and the positive charge. They want to get together and let all the electricity flow, and that's going to be the lightning bolt, but it doesn't do it instantaneously. They have to slowly work their way through the atmosphere, because remember, the air does not want the electricity to flow. It's an insulator. It's a bad conductor of electricity. So in a very few select regions, the electricity, this negative charge in this case, is going to start to make its way towards the ground, and we call those step leaders. They're kind of the advanced scouts of the lightning, and they are kind of randomly trying to make their way to the ground. All right, they can feel the ground, They know the ground is there and they're desperately trying to get there. As they start to get close, the charge in the ground, which is not nearly as strong, starts to feel that negative charge coming down. So in this case, the bottom of this cloud was massively negatively charged. It's sending out these step leaders down to the ground, these little tendrils, the first advanced scouts of the lightning. As it gets close to the ground, the positive charge in the ground says, oh boy, I feel some negative charge getting close. And it starts to itself come up from the ground because it wants to meet and form a lightning bolt. Look at that, here they come. Okay, so he calls these upward positive leaders, and I apologize, I keep advancing too quickly in this video because I do want you to see what happens here. So there you go, these upward positive leaders. All right, see that? The negative charge is coming down, the positive upward leader is coming up. Eventually, when they meet, that closes a circuit. As soon as they close that circuit, all the electricity in the cloud can discharge and come down to the ground all at once in a massive discharge of electrical current. And that's really the lightning strike. It happens so fast that you don't see these step leaders or these upward leaders ever coming. It's too fast for the human eye, but I'm going to show you a bunch of videos where they slow it down and then you can really see it happening. But as soon as they make some connection, then all the other step leaders are not necessary. Once the cloud is on one path, the ground, all the electricity will go into that one path. And that'll be the path that it prefers, and the other ones can just go away. Right? So that's the connection right there of the upward leader and the step leader. It feels it, boom, and there's the flow of electricity through that now open channel. So you can still see, right, some of these downward leaders and some of these upward leaders here, but we call this one main flash. This is called the return stroke. The circuit has been completed between the high voltage in the cloud and the lower voltage in the ground, but all the electricity can flow now through this super hot filament. This is a big channel of ionized gas that has now become a conductor. Once the return stroke has formed, this is a conducting channel of air and electricity flows through it very, very, very easily. If you want to know why that is, it's because it's so hot and energetic that all the molecules of air have had electrons ripped off it so that they now have a charge themselves, and that means that they are a conductor of electricity. So look at that, just beautiful picture. And then boom, you know, that second return stroke right there. So this is a cool picture as he shows, you know, you have your main return stroke forming there, but look at this little upward leader over there. See how it was wanting to connect? Here's the step leader coming down and this upward leader kind of wanted to connect. It just didn't get there first. If this had not happened over here, this would be a lightning bolt in another instant, right? As soon as these two connect, this would have been the main lightning bolt. It just didn't happen early enough. So that's the way. And then take a look at this. Here's another one, main lightning bolt. Here's another upward leader right here. Again, it just didn't connect in time, but whatever this thing is hitting, there's a bunch of little upward leaders coming off it. Pretty cool. And then take a look at that guy, right? So same kind of thing. So we'll show another example here. So this is what lightning really is. It's an example of a cloud to ground lightning flash. So this is going to be a negative flash. Let's go ahead and take a look. Sorry, I'm just having a little trouble with the video here. Let's pause it there. All right. Negative step leaders coming down from the cloud. You can see it looks random. It's like little tendrils. The electricity is trying to find its way down. It's going to just find whatever it can. Now on the ground, in this case, there's a radio tower. This is why really tall things are dangerous in a lightning storm. All the positive charge in the ground wants to get up in the air. And so of course it's going to find its way through the ground to the highest thing there. And radio towers, the top of your house, steeple of a church, something like that, they're way up in the air. All the positive charge is going to accumulate there, and you can see this positive upward leader right here. See how it's starting to flow? The negative charge is trying to work its way to the ground. The positive charge, in this case in the radio tower, feels that, and it's actually throwing a positive leader up into the air. And when these two meet, it'll be a huge flash of lightning with a return stroke. So let's see what happens. Okay, can you see how much brighter it's getting now? It's getting brighter because they're starting to get really close to each other. A lot of electricity is starting to cram up into these things. Still not as bright as it's going to be when they actually meet each other. Boom, there you go. And so bright when the return stroke happens, that whatever camera you use to take these pictures, it just gets saturated. Right now, we're going to see it doesn't damage the camera, but it's so bright, there's just no details going. It's so much energy in these lightning strikes, unbelievable amounts of power and energy. Finally, it dims, and look at that, beautiful, beautiful lightning strike. Let's just see this again. Negative step leaders coming down, positive upward leaders there. There's that return stroke. And then there's the lightning bolt, right? So all the rest of it you would never see. When the lightning flashes, by the time you look at it, all you're going to see is this one bolt of lightning. But now you know there's really a lot of little fingers. But note the little leaders are gone now. All the electricity has been connected through that one ionized air channel from the ground to the cloud, and all the electricity flows to that. All the other leaders can then go away. All right, and that's just another cool picture of the lightning again. So when you see it in real time, you don't see any of those things happening, but you just see that one bright hot channel of gas. So how hot is that channel? Well, it's really, really dangerous, my friends. The lightning strike can be around 50,000 degrees in temperature, at least. It's hot enough to blow everything apart. That's why these thunder booms are so explosive. That lightning strike can be at over 1 billion volts. Remember we talked about voltage, guys, the 9-volt batteries. The battery that powers your car is 12 volts. The house and your electricity is 120 volts. Everything you plug anything into in your house is 120 volts, except for a few circuits in your house, like your dryer is probably running on a 240 volt circuit. That's probably the strongest voltage you're going to ever experience in your household lifetime, 240 volts. A lightning strike is like 1 billion volts. It's so much power and energy. It just crams so much electrical energy in such a small space that it just heats everything up to these extremely tens of thousands of degrees, rips the atoms apart molecule by molecule, rips the electrons off of the atoms, creates this explosion, right? And that's what you're hearing in the thunder. That's why the thunder is so loud. This air goes from just being normal air like you see around you outside. In a blink of an eye, and of course faster, it goes from that normal air to something that's at like 50,000 degrees with 1 billion volts of electricity passing through it. And so that air just expands and it causes a supersonic shock wave. It's a blast wave. That's really what the thunder is. The thunder is a supersonic blast wave that's coming off of this instantaneous disintegration of the air caused by the massive flow of electricity. That supersonic blast wave propagates outward from the lightning strike and propagates through the air, and we hear that blast wave as thunder. Right? And then sometimes you hear the echo of thunder like we're hearing there. So it's really, really loud. That thunder boom is really loud. And that's just because there's so much energy being released in that lightning strike. And here is another great picture. If you look at what's happening here, again, you guys know that here's this return stroke, you know, from the cloud to the tree, it's connecting it. And look, where did it hit? Yeah, the highest thing in this picture. There's a house here. There's a fence post in the foreground, but look at these trees. And where did the lightning hit? Did it choose to hit on the ground over here? No, the top of the tree. The top of the tree is the highest place where that positive charge can work its way up and make that jump up into the clouds. So this is why in a lightning storm, if you ever have the bad misfortune being a lightning storm, you really don't want to be near a tree out on the open ground. If it's like an open golf course, the lightning wants to come to the tree. But if you're the tallest thing in the middle of a golf course, it really wants to come to you as well. So a lot of times they would advise, if you really think you're in danger of lightning, if you're laying flat on the ground, that's the best place to be. I'm 6 foot tall. If I'm standing in the middle of an empty field for miles and miles and miles, and I'm standing in the middle of the field, well, guess what, friends? I'm the tallest thing in that field. I'm 6 feet above the ground. I'm going to be the easiest way for that positive charge to leap up to the cloud. And you're in very real danger of being a victim of a lightning strike, which can absolutely be fatal. So you really can't mess around with the incredible power of thunder and lightning, and you really have to be careful. It's no joke. It is the power of nature that really, really needs to be observed and respected. Absolutely. So now that we understand about, let's watch a couple of these in super slow-mo. This is a view of lightning that you're never going to get in your life because your eye just doesn't work this fast. But we're lucky we've invented really fast cameras now that can do it. All right, so look at all these leaders coming down. Is one of these going to become a lightning bolt? We don't know. It looks like they're working their way to the ground. Some of them are going off to the right here. Some are coming to the ground. Looks like something's going to happen. And then finally, whoa, there it is. There it is, right? Something finally connected to the ground. So this guy won, if you want. It's not a race. The leaders are not racing each other. They are just moving as quickly as they can, randomly trying to find the ground. Something I should point out here, as you watch all these leaders come through, we're going to watch a few more slow-mo videos. Just keep in mind, this is not gravity. So you might think, oh, gravity has something to do with it. The lightning bolt is coming from the cloud down to the ground. Gravity has nothing to do with it. That's why you're actually seeing some of these leaders going from left to right. They can move horizontal. They can actually move up if they want. It has nothing to do with gravity. It has everything to do with the fact that the bottom of the cloud, which is high, has one charge, and the ground has a different charge. So yeah, those leaders are going to come down to the ground, but it's not gravity driving them there. They're not falling. They're kind of randomly walking through the air. They can feel the potential. They can feel the voltage difference ahead of them, and they know they want to get there, but they have to kind of take this curving, meandering path to actually get there. So that's a good example of a very cool, some leaders and a lightning strike, and you can still kind of see this one here. Let's take another look of that. Let's see now, let's see if you watch this in super slow-mo, let's see if you can predict which one of the leaders coming down is actually going to turn into the lightning strike. Kind of hard to do. Let's see if you can do it. Okay, there's some happening over here. Okay, something's happening. No, there's a lot of flashes. Like, look, so this is like within cloud. You can see lots of within cloud flashes here. Like, here are the leaders. Some are going up, some are going sideways. Something's coming down. Something's coming down. Something's coming down. Look, it's almost happening. Now, I don't know actually which one of these it actually hit first. It's connecting with something, but now you can see, look, as soon as it touches the ground, look how much brighter the channel gets. It's opening up the electrical current from the ground to the cloud to form this return stroke here. Let's just see what happens. Bam, again, boom, so bright, beautiful picture, beautiful, beautiful picture. It saturates the camera, and all that's left is this one ion channel. All the other leaders are gone. All the electricity is dissipated through that one channel. And look, it just hangs around for a while as that column of air cools and dissipates. Absolutely fantastic video of a lightning strike. Again, a view of lightning that you're never going to see in your day-to-day life. Your eyes just don't work that fast. Let's take a look at one more. Again, let's see if you can predict where the strike is going to come. Okay, there's a lot of stuff going on here. Looks like a lot of stuff happening here. Can you see these flashes? Something's happening over here. It's very dark now. It's a night. Can you see these? Let me just pause it here. Can you guys see down here? I don't know if you can see, there's like one or two lights. There's actually like 3 antennas here, 3 radio towers. I don't know if these are cell phone towers or radio towers. There's something happening here. So this is a good candidate. Maybe something might be happening here if the downward leaders can connect with the positive charges on these towers here. That might be a good idea. That might, but I can't say for sure that's what's going to happen. Let's continue. Okay, a lot of energy here. Look at these leaders very slowly making their way through the atmosphere. There's a lot of flashing happening here. They're not connecting to ground, so nothing's really happening. These guys are, there's a little more current in them, right? They're a little brighter. Ooh, but something's happening here. Look at this guy. Look how it gets brighter. It's getting closer to ground. It can feel the charge in the ground. Now it's way ahead. It's way ahead. It's getting closer and brighter. Boom, and there it goes. Look at that strike. Absolutely fantastic strike, right? All of that electricity there. Now, because it's connected the ground to this region of the cloud up here, but this region of charge over here is pretty separate, this leader actually has not gone away because the charge flowing through this lightning strike is actually not coming from this collection of charge here. So the clouds would still like that area to get to the ground. And now look, that chart, look how long, the clock is still ticking here because you can see stuff happening on the right. Look at the lightning bolt on the left. Look at how long it stays bright. This is what your eye can see, right? I said before, your eye is slow. It takes a while for your eye to see something. So this bolt on the left, it just stays bright and stays bright and stays bright. Eventually it will dim. Oh, this is a great shot. This is a great shot here. Now look, here is along with the main lightning bolt you guys are looking at. Now here's this within cloud lightning bolt. This is awesome. This within cloud lightning bolt happening from left to right here. But remember, you can really see these towers down here and see how the towers have thrown up positive leaders. They are desperately trying to connect the positive leaders to this negative charge. Now you might say, oh, Dr. Rehse, why isn't this forming a lightning strike here? I get the feeling that we're looking at 2 different distances. I'm not exactly sure, but you can see the positive leader going up. And I have a feeling that that horizontal horizontal strike is many miles away from this. And so they're actually not connecting in this region because it looks like it should have connected right here. It just didn't. All right, so it's still kind of, look, it's climbing its way up. This positive leader here is amazing, coming off this big tower, going all the way up. And eventually, if this guy could connect, maybe it would form its own lightning strike. That's just absolutely amazing, amazing thing. And the same thing happening up here, right? This must be another tower up here. See these positive upward leaders here that are just seen to start in air? There must be like a cell phone tower there that all this stuff is coming up from. Really cool. Really cool. So that's it, guys. We've gotten through today's lesson. Lightning is electrical charge from a cloud. It's just trying to connect another region of opposite charge, and that could be within the cloud. So you'll oftentimes, like an evening, if you go out, you can see lightning off in the distance. It's just within the clouds. That can happen. Or it can be from the cloud to the ground, but it's a region of charge trying to neutralize itself by connecting with another region of opposite charge. When those charges actually get around to connecting, electrical current can flow from one region to the other to be neutral. That's going to happen extremely quickly and explosively. And when that happens, a massive electrical discharge occurs, and that's what we're going to see as the lightning strike. Because it is so explosive and fast, the thunder is the sonic boom from that explosively fast electrical discharge. And that sonic energy carries for miles and miles and miles. That's why you can hear lightning strikes 10, 15 miles away easily. There's that much power being released in that blast. If you want to know how far away a lightning bolt is, every 5 seconds you have to wait from when you see the lightning to when you hear the thunder will tell you how many miles away it is. So that's just a handy trick that any of you can use to tell how far away a lightning bolt is. Very, very useful trick to have. And lastly, we learned that if you shuffle your socks that are made of wool across carpet, you can build up charge that you can then discharge in a teensy tiny little lightning bolt coming out of your finger, ending on something else that's conducting. It's the exact same physical phenomena. And how cool is that? That's physics for you, folks. So glad you were able to join us today. I really appreciate spending time with you. I hope to see you again real soon. Thank you so much. Bye for now.